By the way, the op-amp 741 has been used for decades. Even when I was in school, we were using op-amp 741. So you can tell, this op-amp 741 is one of the most commonly used and the typical one for the op-amp. There are so many different types of op-amps, right? So even though for our chapter 5 op-amp, right? So we learned how to do there was a table, 5.3, all the formulas, right? So you need to know how to use the formulas. How to use the formulas from the table, including the section, if I remember, 6.6.1 or 2 or 3, whatever, for the integrators and those are integrators. So with those formulas in table 5.3 and then 6.6.1, 6.6.2, those two additional ones, those are the foundation for this class to know about the op-amp. And what Steve is going to demonstrate today here is how the 741 to be in operational mode, right? Actually in the lab situation here. And so I'm glad we have our professional photographer here, as always, in the last couple of weeks. This will be your third video, and I appreciate it very much for Omar's wonderful video. And I already got his YouTube. I will post that into the canvas, into the module in somewhere. I will announce that later. So anyway, so yeah.
Okay. All right, so this is the op-amp. It's a little box. It is designed to bridge the gap in the breadboard. So if you remember, it will be like 5 dots in a row, and there's a line, and then another bank of 5. So the op-amp is going to sit across this divide And that way you have the 8 pins coming off it going to 8 separated rows to break it out. So 1, 2, 3, 4. So that's what I have on the breadboard right now. There is, depending on the op amp, there's a little notch at the top or a circle to indicate which pin is number 1. So the top left is 1, or this circle is next to the number 1. And then it counts anti-clockwise around. So 1, 2, 3, 4, 5, 6, 7, 8. I have labeled them. So this is the inverting input. Call that an input. This is the non-inverting input. This you're not going to use, so we can ignore it. Pin number 4 is the negative power supply.
Zoom in.
So you're going to put minus 15 volts on this pin. 5, we're not going to use. 6 is the output. 7 is the positive power supply, so we're going to put plus 15 volts here. And then 8 we're not going to use. Okay? So the way I have this set up is I have an input, so let's just call it my signal like that. I have a resistor, we're going to call it the input resistor, going into pin number 2. So we'll put it here. So in this specific example, this is 10K. Then I've also got between the output and that inverting input a 20K resistor. So pin 6, and we'll go up here and down to here. And this is your feedback resistor. I'm not sure what you've covered in class, but the formula for these, if you say A is gain, it's going to be equal to negative the feedback resistor divided by the input resistor. So in this case, we can all do that math. It's 20K divided by 10K is 2. We put a minus there because we're using the inverting input, so it's going to come out the opposite of the input. We can actually show that, hopefully. Nope. Okay. Actually, twice as big. Yeah, makes sense. So on this screen, the yellow line is the input, and we're showing 1 volt peak to peak. And then the green line, you can see it's a mirror image, and it's at 2 volts peak to peak, which makes sense because we just said our gain is 2. So this is the signal path, the input with an input resistor, a feedback resistor going from 6 to 2, and this is your output. But the op amp cannot just produce energy for no reason, so you have to power it. We're doing that with pin 4. So if I've got a DC power supply, and it has 3 options. It has a negative output, a ground, I'll call it G, and a positive output. I'm putting the negative up to 4. I'm putting the positive, wherever I said, up to 7. And then also I have my ground, which I'm using as the ground for the entire circuit, because the ground needs to be the same for everything. And we're going to use this on the non-inverting input. Because what the op amp is trying to do is take the difference between the 2 inputs and then output an amplified signal or a divided signal or whatever else. It can do lots of things. It's called an op amp because it can calculate a lot of operations. If you've ever heard of analog computing, which used to be a big deal, and maybe will be a big deal again, don't know. This is how you would do math. So I want to multiply something by 2. I input the first number that I want to multiply by 2, and then the output tells me what that number is, multiplied by 2. So you can directly calculate things using it. Okay. That's all the connections, I think. Yep. So the DC power supply the way this is going to get set up, we've talked about it before, but just so we go over it again. These top left three, they say +6, +25, -25. So we've been using +6 prior to this. And in this case, we're going to hit +25 and set the limit to 15 volts, 100 milliamps, like normal. Then you hit the -25, you got -15 volts, 100 milliamps, like normal. And the ground is just the ground. Turn it on, and we end up with this. So it's working. The one thing that this lab asks that I don't think anyone goes over is it asks if there's a saturation effect present. So the op-amp can only amplify up to the voltages you provide. So you've given +15 volts, -15 volts. It cannot give you +20 volts. There's no way for that to happen. It can't even give you +15, but ideally it can. So if we are to increase the input signal, I can't actually increase it enough. Hold on, I'm going to get another resistor. Oh no, I can do it another way. This way's better. So I'm going to reduce the power I'm providing to the op-amp now. So, +25. No, that's not what I want. Okay, so we can see it pretty well there. So if I go to 2, increase this, you can see that this is attempting to amplify further than the power rail, is what you'd call it. So it's hitting up against what is the maximum value that it can amplify to. So when it flattens out like that, that's distortion, that is the saturation effect, that's what makes guitars sound cool. It's everything. But that's what it's looking for when it asks for that in the lab. Aside from that, that's pretty much it. This lab almost constantly doesn't work. Whether that's because the op-amp is broken because somebody has burnt it and put it back, or what, I don't know. But if you run into trouble, I guess next Monday, just rebuild the circuit. It's not a very complicated circuit. Just rebuild it somewhere else on the breadboard, rebuild it on another breadboard, use a different op-amp. Just go through all the little things that it could be, and you should work it out. And that took no time. Any questions?
Sorry, what is the 10 kilo ohm connected to?
So this is your input resistor.
Yeah.
If we don't have that, then we wouldn't have, it's just like this is a simplification. It's a calculus problem, really. If we didn't have the 10K, I'm not actually sure what would happen. Let's find out. And also, let's put this back. Come on, buddy. Okay, put that back. Where'd you go? Well, the answer seems to be it's not working, which that works for me. But one thing we can show, the reason for this feedback loop, the reason it's so important is without it, the op-amp will just try to increase the gain to infinity, as close as it can. Ideally, the gain of an op-amp, without putting in a feedback resistor or anything, would be infinite. So, if we remove that, we should get massive saturation effect, which I think is what we're getting. If it exists. Nothing happens at all. Doesn't make any sense. Well, it should be working. Either way, it's not. The point is you need the feedback resistor and the input resistor in order to tell the op amp what you want the gain to be. So I have a 20 in here. It could be a 30, and then it would be multiplied by 3. I could have a 100, it would be multiplied by 100, up to the power that I'm providing the op amp. Okay. Any other questions? No. Is everyone comfortable with the equipment?
Yes.
It's going to be these two that you're using. Keep in mind, please, that the function generator is not going to show up on the screen unless you put a probe on that. Like, they are not connected at all. This is a little thing down here. It's all on its own. So right now I have channel 1 connected to the same place right here that I have the actual input of the function generator in. One other thing is these two grounds are internally connected, so don't feel like you have to connect every single ground to the same ground and you end up with this horrifying mess of octopus stuff. These will take care of themselves. This one, I do not believe, is connected to these ones, however. So at least one ground from here, one ground from here, and this ground need to be connected. More questions? Nope. All right. I'll call it there then.
Can I see the connection? I mean, just because we see.
Yeah. I mean, you want to take a picture of it, whatever. It doesn't bother me.
I'll do it for the video.
It's kind of difficult to see. Let me pull this guy out of the way. Ignore that. So this guy is my input resistor. This is my feedback resistor. And you can also see, maybe, there's a very tiny circle in the top left corner of this.
I can't catch it on video.
Yeah, fair enough.